So in section 2.6 we're going to do something similar, but we're going to talk about the second derivative and inflection points. So let's see what this is about. The second derivative is the derivative of the derivative. We're just going to derivate twice. We call it f double prime of x is how we read this. It says of a, either way, a or x, just using a different variable here, is the limit as h approaches 0 of f prime of a plus h minus f prime of a over h. We had several notations for the first derivative. The second derivative has some as well. F double prime of x, d dx of dy dx, the derivative of dy dx. We could also say d dx of f prime of x, and then the second derivative d squared y over dx squared. So again, we'll be using some of these notations. These all mean the derivative of the derivative. So what's the relationship between f prime and f double prime? Well, this is exactly the same as the relation from f to f prime. So we said if f was increasing, f prime would be greater than 0. Well, if f prime is increasing, then f double prime is greater than 0. If f is decreasing on an interval, then f double prime is less than 0. Exactly the same as the relationship from f to f prime. But then we want to look at the relationship between f and f double prime. And in this case, we're going to start talking about concavity. So looking at the original function and the second derivative. When f is concave up means that it is, curving in this direction. Concave up. When f is concave up, then f double prime is greater than 0. When f is concave down, then f double prime is less than 0. Okay? So this is going to be the relationship from f to f double prime, and you'll see how this builds in a second. A point of inflection occurs when concavity changes. So when concavity changes, f double prime is 0. So from f to f prime, we were looking at max and minimums, created a 0 first derivative. Now in our function, the point of inflection causes a 0 in the second derivative. So a point of inflection, if I have a function that looks like this, and it's going from concave up to concave down, somewhere in the middle here it changes. It's going up, 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 curving up, and then it flips and it's curving down. This would be a point of inflection, and it would be point of inflection, and it means that f double prime of that point will be 0. So whatever that x value is at the point of inflection, we're going to get a 0. All right, let's see if we can put this together. So I have 3 graphs here. The first one we're going to look at is function a, and a is f of x. So try and draw a sketch of this. I know there's a lot going on, but we're going to put these pieces together. So the red function is f of x. Now let's remember what we talked about with our original function. When I have a maximum, and there's a small maximum here, it comes increasing, 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 and then it kind of turns a corner and it starts to decrease just a little bit. So this is a local maximum, which means that at this point, my derivative, which is graph B, has a 0. And you notice that my original function f of x was increasing. Let me get a laser. So it's increasing all the way up here, increasing, increasing, increasing until it gets to the top, and then its slope is 0. Look at my B graph, my f prime, the whole time f is increasing, b is positive. And you can see it follows. These are small positive slopes here, small positive numbers. The slope gets steeper and steeper. The positive numbers get higher and higher. So right about here is my biggest slope, my biggest positive. And then you see the slopes stay positive, but they get smaller and smaller to my 0. And the slopes come back down to 0. From this point on my function, I am decreasing very slightly, and you can see I have very, very small negatives down here. So again, function f is increasing, so my derivative is positive. When my function reaches its max and starts to decrease, my derivative has a 0 and starts to become negative. All right, let's now look at my green graph compared to my C, and C is going to be my f double prime. So let's look at the B relationship to C. Again, we're talking here about increasing and decreasing and maxes and mins. So as I follow my green graph, I get to a maximum here. Oh, stop jumping around. I get to a maximum here, which is going to cause a 0 in my second derivative. My first derivative increasing to 0, and then my first derivative then decreases for the rest of the time. So let's again get my laser out here. So again, looking at my f prime, increasing, 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 increasing to my maximum, which is going to give me a 0 slope, a horizontal slope. All this time that f prime is increasing, f double prime is positive. Then f prime decreases, and during all of that time, f double prime is negative. And you can see that the steepest negative slope corresponds with the lowest negative number in f double prime. All right, let's go back to our original function now and talk about our concavity. So in the original function, this whole part here to about here is concave up. Then it changes to concave down. The point which I change is called an inflection point, point of inflection. That creates a 0. Look, now I'm jumping from f of x down to f double prime. So look again. When f is concave up, curving upwards, f double prime is positive. These are all positive numbers. When it starts to change, when my original function starts to become concave down, my second derivative has a 0, and it turns into negatives. And you notice it's a pretty steep concave down here, which is a steep negative, and then a very gradual concave down through to the end. So let me see if I can summarize this in a table. So if f of x, f prime of x, and f double prime of x. So if f of x is increasing, f prime is greater than 0. If f of x is decreasing, f prime is less than 0. If f of x has a max or min, the place where it changes from increase to decrease, f prime is equal to 0. Now, if f prime is increasing, f double prime is greater than 0. If f prime is decreasing, f double prime is less than 0. And if f prime has a maximum or minimum, then f double prime equals 0. We also have a situation if f prime of x is concave up, then f double prime is greater than 0. These don't necessarily have to happen at the same time. But if we look at our original function and it's concave down, f double prime is less than 0, and if we have a point of inflection on our original function, then f double prime equals 0. We're going to do lots of practice on this. Okay? The last thing we're going to do in this section, and we'll work on this together in class, is derivatives as rates of change. So if a function f of x represents distance in terms of time, then f prime of x will relate to velocity, and f double prime will give you acceleration. So let me draw a brief picture here. So let's say that this is distance, that this is time, and this is distance. So I leave my house and I speed up and I drive real fast, and then I slow down, and after 2 hours I've gone 60 miles. Okay? The rate of change at any point on this graph, if I took a slope here, my rate of change, remember that's change of y over change of x is my slopes. So my first derivative will be distance, come on, back up for me, will be my distance over time, my miles per hour, let's say this is hours and this is miles. So miles per hour, which is my acceleration. Okay? Or which is my velocity. F double prime is going to be f prime over time, which is going to be my miles per hour squared. That's acceleration. Okay? Jot this down. We'll be working on this together in class, but that's it for the video.